Now let's try to understand how a typical bulk CMOS technology looks like. So to get a clear picture, I will show the cross section of an IC which has been designed in a bulk CMOS process. Most bottom layer of the cross section, you will see substrate. And this substrate will be a lightly doped P-type semiconductor. And on this substrate, you will be seeing these active devices and MOSFET and P-MOSFET. So just looking at the N MOSFET, it will have these N plus diffusion pockets acting as source and drain. Then there will be gate oxide. And on top of the gate oxide, gate is formed with the help of a high conductive material. So many times it can be a highly doped polysilicon which has been deposited, or it can also be some metals. So this is how the cross section will look like around the substrate. Now we understand that this is not sufficient for creating circuits with thousands or millions of these kind of active devices. We also need interconnection between those elements. So this interconnection is done with the help of metallization these are metal, and many times this metallization is done using copper. So now we can see that if there is a requirement for interconnection, it can be done with the help of these metals. These metals can form contact with each other with the help of this metal to metal contacts called PS. And all this space between these metals is filled with an insulator, and in a CMOS process, the insulator is silicon dioxide. It also called as interlayer dielectric, and this is formed using silicon dioxide. So if you look at this cross section, you'll see that starting from the substrate, we are going till the metal layers. So this metal thickness will be of the order of micron. So this lower metals, you'll find that maybe some 0.2 to 0.3 micron. Similarly, the gap between the metals is also going to be of the similar order. Whereas as we go to the top layer, it is possible that the thicker metals are available, and these thicker metals will be of the order of few micron. It can be anywhere from 1 to 3 microns available. So when we are dealing with a CMOS process, this stack is already available. So any device which we are trying to fabricate, in addition to the active devices, also have to use the same stack. When we talk about the passive devices, mainly we'll be utilizing these metals, contacts, and some extra conductive materials which may be available near the substrate. Let us start with an inductor in CMOS process. Let's see this symbol of the inductor, and the voltage and current for this inductor are related as V is equal to L di by dt. So the inductor develops a voltage every time current is trying to change, and this is happening because there is a magnetic field associated with the inductor whenever there is a current flowing through the inductor. So in general, any circuit element which has magnetic field associated will be showing this kind of inductive behavior. So when we talk about inductor design in a CMOS process, then the simplest way we can try to realize an inductor is by just taking one of those metal layers which are available and draw a thin line over there and allow current to flow. So when there is a current flowing through a metal, we know there will be magnetic field associated with this, and the magnetic field will be like this, going inside the plane on the bottom side and coming up from the top side. We can now associate this magnetic field with this simple piece of metal. Every time this current is trying to change, there will be a voltage developed across it, and it is going to act like an inductor. So this is the simplest way we can realize the inductor on chip. And if you realize these inductors, you will find that the amount of inductance which we are going to get will mainly depend on what is the length of this metal strip. Inductance is going to be proportional to the length of metal, say metal wire or metal routing. Okay, so if we take an idealized situation where we have metal wire, the metal wire is really thin, the return path is not visible. In such a scenario, we'll find that this inductance per unit length is approximately equal to 1 nanohenry per millimeter. Let's say we want to have an inductance of 1 nanohenry, then this entire length of this metal has to be equal to around 1 millimeter. So when we are talking about realizing these inductors on chip size is going to be few millimeters. So already we are talking about IC, which is of this few millimeter square kind of area. Inside that, if we want to realize 1 nanohenry, that itself is taking requiring a long length. It is having some problem with the form factor, because if we just realize an inductor with a straight wire, these terminals which are available are really far apart. So if you want to connect any device to this inductor, again we have to make long routing. So this long routing will also add its own inductance. So to make the inductor practical and to fit nicely on an IC, normally these straight-wire inductors are not preferred. So we want to bend these wires to improve the form factor of the inductor. So instead of talking about straight wire, now we can talk about a wire which has been bent so as to improve the overall form factor. Bring terminals. Okay. Improve the form factor. This is done so as to make the inductors more practical. Now we can see that the moment we have bent the metal into this shape, so again when the current is going to flow, there will be magnetic field associated with this inductor. Now when we talk about current flowing in this direction, let's say coming out, now the magnetic field will look like this, where fields are entering the plane in the center of this loop and coming out from the outside. Now let us try to find out what will be the inductance of this wire which has been bent in the form of a square loop, ignoring the other routings and just bringing these two terminals very close to show that current can enter and exit from these terminals. We can also draw the corresponding magnetic field associated with each of the segments of this loop. Say and because each of this segment is going to have its own associated magnetic field, we can easily find out what will be their individual inductance. So for example, this one I can call as L1, L2, L3, and similarly L4, talking about this entire length. Right now it looks like as if we have put 4 inductances in series and then trying to find out what is the overall inductance. So our basic intuition says that the effective inductance should become L1 plus L2 plus L3 plus L4. Okay, so that would have been correct, but there is some extra detail which has not been shown while drawing this magnetic field diagram. The detail is that when current is flowing, for example, in the leftmost segment, it is creating this magnetic field. But in addition to that, there is also a magnetic field which is coupled to the L3 segment. And this is going to happen for all the other segments as well. Okay, so whenever there is a magnetic field associated, part of it will be only linked to that wire segment. In addition to that, there will be part of the magnetic field which will also couple to other segments. And the way I am showing you, you can easily see that L1 will only couple to the L3 because it is orthogonal to L2 and L4. And similarly, L2 will only couple to L4. So in addition to just showing the self-inductance of each of these segments, we also need to be careful about the mutual coupling. So I can say there will be some K13 in this manner. Similarly, K24. So now when I have to find the effective inductance, L effective will be first the summation of each of these inductances plus the effect of mutual coupling. So this K13 will give rise to a mutual inductance M13, and this M13 is going to effectively reduce the inductance of this L1 and L3 combination. And similarly, when there is a current which is flowing in the L3, there will be again a mutual inductance M13 coming into picture, which is going to again reduce the effective inductance. So we'll be seeing this term 2 times, and similarly we will be seeing this minus M24 2 times. This K is the coupling coefficient. And this coupling coefficient depends on the geometry. So here the K is 0 because they are orthogonal to each other, whereas when they are directly aligned with each other, we are going to get high value of coupling coefficient. And you may be already knowing that this M13 is going to be equal to K13 square root of L1 L3. So if I rewrite the effective inductance of this square loop, it is going to be, let me call this summation as some L sum, and assuming that these mutual inductances are going to be almost same, I will be getting minus 4 times M. So if I had just a straight wire of the same length as the perimeter of this square loop, I would have got an inductance of value L sum. But since we have to convert the straight wire in this square kind of form, mainly for practical reasons, we see that the effective inductance is coming down because of the mutual coupling. Here, plus L2 plus L3 plus L4, M is equal to M13 is equal to M2. And if we have to draw an equivalent circuit showing each of these individual inductances separately, we can draw a circuit with L1, L2, L3, and for simplicity, I am just showing that these terminals have been taken from one side. Anyway, going to be in the series, these two segments. So whether I take here or here should not make any difference in our conclusion. Now we know that this L1 and L3 are coupled, And to show the coupling, you can add these dots since they are going to be facing each other directly. So the dot is going to be like this. This is K13. Similarly, for L2 and L4, the dots are going to be in this manner. This is our L effective. The conclusion is, if you want to maximize the inductance, you should make sure these segments are as far apart as possible from each other so that this reduction in the inductance because of mutual coupling doesn't affect the effective inductance of the loop. Inner area enclosed should be I to minimize coupling between the segments. Here it implies that L effective is going to be proportional to the area enclosed or the inner area. This is a very important intuition which we need to keep in mind when we are trying to design this kind of inductor loops. So higher the loop area, more will be the inductance. We also know that whenever we are trying to design inductor using metal, there will also be this resistance in the metal routing. We can talk about the quality factor of inductor. So quality factor of the inductor, inductor we can define as how much of energy is stored by the inductor in the form of this magnetic field normalized by the amount of energy which is dissipated because of this resistances which is present. This is equal to 2 pi into energy stored. I should say peak energy stored, because this inductor may not be always at resonance. So the Q inductor is going to be 2 pi into peak magnetic energy stored divided by energy lost per cycle. And the simple model for such an inductor is by adding all these resistances in series and say that some R loss is present. So if we find the Q of this inductor at a given frequency, then it is going to be equal to omega L effective divided by R loss. So the Q of this inductor can be very easily derived by assuming that current I is going to flow at frequency omega. Then the energy stored at any time is going to be half Li square. So the peak energy is going to be half Li peak square, and this energy lost per cycle similarly can be derived as some I peak square by 2R. So you'll find that you'll be getting this simple relation for the quality factor of inductor at any frequency omega. So here L is coming in the numerator, R is coming in the denominator. So if you want to maximize the Q of an inductor, inductance has to be increased while reducing the resistance. L effective is proportional to the inner area, whereas this R loss, if we see, it will depend on what is the length of wire being used. So more the length, higher will be the resistance. So in a way, it depends on the perimeter of the inductor, whereas the effective inductance depends on the inner area. So this is the perimeter. So it implies the Q of an inductor is proportional to the inner area to perimeter ratio. So for a given inductance, if you want to maximize the Q, we need to make sure this ratio is maximized. So out of all the shapes which we can think of for designing an inductor, it turns out that the shape which maximizes the inner area per unit perimeter for a given inductance is a circle. Circular shape maximizes this ratio the given A inner. So this is really important, and this can be a very good guidelines for trying to design these kind of inductors.